Alright guys, so welcome back. This is video 21.1, so it's the start of chapter 21, which focuses on various topics like electrical potential energy, potential difference, and then the idea that we won't get to in this video is capacitance. There'll be a whole other video next week for that. So in chapter 21, one of the first ideas we talk about is electric potential energy. So let's just talk about other potential energies that you're probably familiar with, such as gravitational potential energy. So if you read through this slide, it talks about it's possible to store potential energy in a system, and you're probably familiar with like a roller coaster. So a roller coaster is getting pulled up the ramp by a chain. And there has to be work done on the roller coaster to give it or increase its gravitational potential energy. So if it starts on the ground, it's not going to fall anywhere, so the potential energy is zero. And as work is done to it, it gains potential energy in this idea. So if we kind of do the same idea here for this question, it says you're going to lift a book at a constant speed. So it's starting here and it's moving up to the higher point. And what happened, or what statement is true about the work done on the book by your hand, and then the change in gravitational potential energy of the book. So here are your options. I'll give you a second to answer. And the correct answer is C. So the work done on the book is equal to the change in gravitational potential energy, and those are both greater than zero. So one of the ideas for work, it was FD cosine theta. So if we look at this idea, force is just the amount of force. D is the distance that it moves, so like that would be the distance maybe that it moved up, and then the force is going up, and so there's a displacement up. And cosine theta, theta is the angle, and this is important later, but the angle between the force and displacement. So they are pointing the same way, so that cosine of theta would be zero. So my hand did positive work on this book, and because of that, if we look at the change in potential energy down here, the height is zero. Up here there is some height, so the potential energy final, or UG, at the end compared to UG, that's supposed to be U in the beginning, there was a gain on energy. So like the hand put energy into the system. That's what's happening. Okay. So conservation of energy, we've talked about that, or you probably talked about it in your previous classes. So again, the gain of the potential energy is equal to how much work is put into the book in this case. We could also talk about like elastic or spring potential energy. So if the spring isn't compressed very much, it doesn't have much potential energy, but as you push in, you do work on the spring, and because of that work, you're giving it more energy. So again, conservation of energy idea, just a different potential energy. So, so a charge has potential energy when it's around other charges, or it's in an electric field. So if we think about this, we have a charge Q here, and we're going to push this charge towards these other charges. So obviously, like charges try to repel, and as they try to repel, the force would push away. So the electrical force between this charge, our charge here, as we get it closer to these other charges, they would try to repel and push away. But kind of like the Earth, like as the book wants to be down on the ground at height equals zero. In order to lift the book up, we have to do work. So this is us. This force over a distance would be the work that we're doing. So we're adding energy by putting this charge close to these other positive charges. Here's an example that I'm going to use for several slides. So we have a charge here at position A, and we're going to move it towards position B. And we have what's called a parallel plate capacitor here. I think I mentioned this in class, but you might not have remember it. But a parallel plate capacitor is a device where it's two metal plates and they are charged, so they're hooked up to like a battery or something, and one plate becomes positively charged, the other plate becomes negatively charged. If we put a positive charge in between them, which plate does the positive test charge want to move towards? So where does this want to go? So if I just let go of it, where would this charge move? So again, let me give you a chance to answer. And the correct answer is it would try to go towards the negative charge, right? So the positive and negative would attract, so it would naturally move that way. That's, again, sort of like the gravity idea. It's just instead of moving, like naturally wanting to move down, it would naturally move to the right. So, so the next question is, to keep the positive test charge away from this negative plate, we would have to hold the charge in place, like this person is holding it in place. When does the positive test charge have the greatest electric potential energy? So when I'm moving this, where in that motion, if I'm pushing this charge over here, where does it have the greatest potential energy? Again, let me give you a chance to think about that. Sort of similar to when does the book have the greatest potential energy above the ground? It's got that idea. So the idea is when it's closer to the positive, again, just like we talked about with that example with the positive charges, when it's close to this positive plate, it has a greater potential energy because it wants to move away, but you're holding it in place. You're holding there just like the book, and it can't move. And when it's farthest away from the negative, because that's like the ground. So if you think about work in this case, we're going to push this charge from A to B, and we're going to push it through a distance that I called D. So we're going to call this charge Q, and the distance between point B and point A we're going to call the distance D. So again, using that work equation, work equals FD cosine theta, where theta is the angle between the force and the displacement. We can talk about the force that you have to apply is equal to QE. So like in order to move it, we would have to take the charge and the electric force in a the electric force acting on a charge in an electric field is this equation. So Fe equals Q times the electric field. So the electric field is going to the right, the charge is Q, and the distance we're moving is to the left. So so the idea here is that it's QED. So QE to replace the FE, D is the distance we're moving it, and then cosine of the angle. So the angle between the direction of the electric field and the direction the charge is being displaced is negative QED. So I'm going against the field, so that's kind of why it's negative. So they're in opposite directions, so cosine of 180 is just a negative 1. So if we look at the change in electric potential energy between points A and B, the potential energy increased by the amount of work that was done on the charge. So like it took the energy out of me, which is this negative QED, and it put it into the system. That's the idea. So so change in potential energy is equal to QED, where D is the distance that the charge is moving in a uniform electric field. Q is the amount of charge that you're moving, and then E is that electric field strength. So that's dependent upon the capacitor. Okay. So we also talked about the electric field created by a charge. So so E, the electric field created by a charge at some point away, is KQ over R squared. We can use this E in our electric potential energy equation. So if we use UE equals QED, we get this equation down here. So if we plug in this value into here, and then R and D are essentially the same idea. So R is the distance between them, and D is the space that you move it. So it simplifies down to K Q1 Q2 over R. So this is the electric potential energy between two charges that are separated by a distance of R. And this is, again, describing the different factors in that equation. So again, just kind of showing you the equations that you're going to use. You just have to use them for the right situations. All right. So the next idea is a little confusing, but it's the one that we use more of. So electric potential, or just commonly known as potential. The one that we use more commonly is potential difference, but they're all kind of interchangeably used. The biggest difference here is this is V for one charge, or the potential energy per charge for one charge, and this is like the change in potential. So you're measuring the potential energy per charge at one point and then another point, and the difference in those potentials will give you what's called the potential difference. So, so this is the formula, the most generic formula to calculate the potential difference. So it's the change in potential energy divided by the charge that you are moving from one point to another. Both potential difference, potential and change in potential, or however you want to call it, are measured in volts. So potential differences cause charges to accelerate. So positive charges always move from higher voltages to lower voltages, and negatives move from lower voltages to higher voltages. So if we come back to this example that we had with these plates, if we put a positive here, the positive wants to move away from the positive plate and towards the negative. So this is a higher potential, and this is a lower potential or voltage. So if you move from one to the other, depending on what kind of charge you have, that would have. And it makes sense if you had a negative, this negative charge would want to move the opposite way. It goes from low to high. So again, we mostly look at positive charges and think about it that way, but we need to know how negative charges are affected too. So the change in voltage would be measured across those, or the potential difference would be measured, the difference between those values. So if this was like at a positive 300, and say this was like a negative 300 volts for voltage, if we started here for the positive to the negative, it would lose 600 volts. If we went from the negative to the positive, it would be gaining 600 volts, because it's like kind of where you start to where you finish again. So potential difference, or change in voltage, is the final voltage minus the initial. So it again depends on which place you're starting and which place you are finishing. So I think I skipped this one. Okay, so batteries are somewhere you might have seen voltage, the measurement unit of voltage. So on batteries, like if you had I don't know, a battery that you might have in your calculator, it's usually like 1.5 volts. And then you'll notice one side is positive and one side is negative. So the potential difference of this battery is 1.5 volts. So what's that saying is going from this point to this point, there would be a gain of 1.5 volts, or if you went the other way, it would be a loss of 1.5 volts. Potential differences are scalar quantities, so you don't have to worry about the direction. It's just really the values that you worry about. You can have positive and negative. So kind of expanding on this idea, so the potential difference, we said, or the change in voltage, is equal to the potential energy divided by the charge. We wrote the potential energy in a uniform electric field as QED, so we can drop out the Q's, and you just get, in a uniform electric field, the potential difference, or change in voltage, is equal to E times D. All right. So again, if we knew the electric field strength and we knew the separation, or how far it's moved, then you would be able to figure that out. Now, that displacement, or that change in position, has to be going from a higher potential to a lower, or lower higher. If I had another point like right underneath B here, which I could call C, if they were at the same location, they're going to have the same voltage, because there's these, in a uniform electric field, there are these places called lines of equal potential. So like if I took the charge and I moved it vertically upward here, it's not changing its location in the electric field. It's at the same like place here in terms of, you know, the distance across the electric field. So it's not changing it there. So it's displacement parallel to the field. So this is perpendicular to the field, so it wouldn't have any potential difference. So if I put, like, that's why you have to measure across the battery to read it. If you put both of like your probes on a multimeter at the same end, it wouldn't record anything. It would just say it's zero. Again, potential is the electric potential energy divided by the charge. That's like the most basic definition. We also just got done saying that the potential is E times D. So if we do, the potential is E times D, and we substitute in the equation for electric field that we had, So the electric field equation was KQ created by a charge, KQ over R squared. Again, D and R are essentially the same thing, so I'm just going to take wherever there's a D and substitute in an R. So if we drop that out, we get KQ over R. So this is the voltage created by a charge. And if we wanted to measure again from one point to another point, we would just have to know where we start and where we finish. So the change in potential, or triangle V, or the potential difference, there's all the same words, is KQ over 1 over RB minus 1 over RA. So if this is A, the initial, and B, the final, it's the difference in those two. If we have an infinite distance away, so if we think of V is KQ over R, and R approaches infinity, what's going to happen to V? So how is this getting bigger and bigger and bigger to an infinitely large number? How does that affect V? So the voltage at that infinitely large distance away would be equal to 0, because you're dividing by a super big number, which would make this number get small, and the voltage would be 0. So if you're super far away from a charge, you have no potential there. But as you get closer, there's a greater potential. So positive charges create positive potentials, negative charges create negative potentials. Potentials are scalars, so you just have to add them. So you can find like the potential at a certain point. It's just like finding the potential and from each of the charges at that point. All right. So this is a nice summary slide. I think it even though these ideas are sort of all interrelated, and you can tell by this concept map, it connects electric force to electric field to electric potential to electric potential energy. So it has all these, like what you're doing to the equations. So you're multiplying by Q as you go to the right, and that's like a blue arrow. You're dividing by Q, or I'm sorry, you're dividing by Q as you move to the right. You're multiplying by Q as you move to the left, and that's the black arrow. And then going up and down, if you're moving down, you have the purple arrows, which that's taking whatever the idea is and multiplying it by the distance. And then if you're moving upward, that's the orange arrow here. That's the only one that does that. And it's dividing by the distance. So it should make sense. So like if we go to electric force and we take force times the distance that the force is acting over, you get the work, or the change in potential, or potential energy. If we take the potential energy and we divide it by Q, we get the potential. That's what we talked about in today's lesson. So V is equal to KQ 1 over R. And then if we took the electric field and we multiplied it by a distance, we would get voltage. So that's another voltage equation that we have. So again, this is all kind of, it's very confusing in the beginning, but hopefully you'll make sense out of it, and it's not too bad. So we will spend more time in this in class, and I'll preview it for you guys if you haven't watched this lesson. But it's really just picking the right equation and when to use it for the different situations that we outlined in the chapter. So we'll practice more throughout the week and in week 5 as well.